Gravitational field qualitative description. So we can write gravitational field. We can write this as region in space where a body experiences where a body experiences gravitational force. Now, look at this definition. If you want to have a gravitational field at any place, there must be a source for the gravitational field. So the source of the gravitational field, the source of the gravitational field is a body. So you can say a body or every object. So every object in the universe is a source of gravitational field. Now, we talk about the nature of the gravitational field. You should realize two things about the gravitational force. Now, we know that the gravitational force has two important characteristics. Gravitational force, there are two important characteristics. There are many characteristics, but these are connected to the defining the gravitational field. Gravitational force, one thing, it is a weak force. It's a weak force, which is significantly weakened the electrostatic force. So, compared to weak force, compared to electric force. So, gravitational force is a weak force compared to electric force. That means that if the mass of the body is small, then the gravitational force is not significant. It is not that it is relevant completely, but it is not very large. Second important thing is that gravitational force is a long range force. Gravitational force is a long range force. So it extends practically to the infinity. Long range force. So this defines these two qualities actually defines the gravitational field, the behavior of the gravitational field. From these 2 points, what we can say is that the gravitational field produced by a body extends to infinity. And second thing, the gravitational force will be very large, close to the body. So we can just write these two things. So theoretically, gravitational field produced by a body extends to infinity because it's a long range extends to infinity. In reality, it may be very weak as you go further because it's an inverse coil of force. It means that just like light, the further it goes, it becomes far reduced, far less. So, let us look at the gravitational field concepts. Now, a gravitational field is represented by gravitational field lines. So, we call it gravitational field lines. Gravitational field lines, or sometimes it is called gravitational lines of force. Lines of force. What does it mean by this gravitational lines of force? These are imaginary lines. There is no real gravitational line. Imaginary lines are used to depict depict gravitational fields. Now, second important thing you need to remember: these lines will show the direction of the gravitational field. Of gravitational field at every point. So a gravitational field line will show the direction of the gravitational field. Typically, the tangent of the gravitational field line is the direction of the gravitational field. For example, if I draw this like this, suppose this is a gravitational field line and it goes like this in this direction. This is gravitational field line. We'll assume that. Then, if you want to find out the gravitational field at any particular direction, this will be the direction of the gravitational field. Or let's make it. Okay, wait a minute. How will that do it? If you want to find out the direction of the gravitational field at this point, this is the direction of the gravitational field. Let's call this point P. This is the direction of gravitational field at P. This is obtained by tangent. You draw the tangent to the gravitational field line, you will get the direction of the gravitational field. And third point that you must remember is point number 3. Wherever the gravitational field lines are crowded, the field will be very strong. So, gravitational field lines are closely packed in strong gravitational fields. Now, let us see how does it look in strong and weak field. Suppose the gravitational field lines, look at here, if these are the gravitational field lines in a region, and in another region the gravitational field lines are like this. This is a strong field. Here, this is a weaker field. Comparatively, it is weaker. Another important characteristic of gravitational field line is this: gravitational field lines never cross each other. Now, why is it so? Now, the problem is that if you have a condition where the gravitational field lines are crossing each other like this, then we have a problem because the gravitational field line shows the direction of the gravitational force. So at this intercepting point, the gravitational field will have two directions. This is not possible because gravitational field cannot have two directions at a point. Gravitational field cannot have two directions because at the intercepting point, the gravitational field will have two directions. But you can have gravitational fields touching each other like this. They don't cross, they just touch each other. This is fine because at this point the gravitational field will be along the tangent. You know that the gravitational field direction is along the tangent because they share a tangent. The gravitational field will be in this direction, which is fine, only one direction. This is the direction of the gravitational field line. And these are the basic concepts about gravitational fields. So gravitational field lines are used to describe the nature of the gravitational field. The important point, we emphasize it one more time. Just remember that gravitational field lines, gravitational field lines. The word is depict the nature of gravitational field at every point. So that is the most important takeaway from this description. And now let us see the two kinds of fields you will be dealing with. Now let us look at here. We'll talk about Earth's gravitational field. So let us talk about Earth's. You will see two different kinds. Earth's gravitational now listen here. If you want to get a picture how do we have it in this way, you just need to think about it. The gravitational field line is obtained by, you need to remember this idea, gravitational field line is obtained by the gravitational force on a body. So if you want to find out the gravitational field at a point, you need to keep a body at that point and see which way the gravitational force act. Now let us take the case of gravitational field due to Earth. So let us draw the diagram and see how it looks. Look here. Suppose it is the Earth. We know that the Earth attracts other bodies because of that the gravitational field lines will be towards the Earth. So gravitational field line, you can see that it starts from infinity because the gravitational field due to Earth goes all the way to infinity theoretically. So I'll mark it like this only on this side. It goes all the way to infinity and it is directed towards Earth. Why is it directed towards Earth? It's directed towards Earth because gravitational force is attractive. If you place a body here, it will move it towards the Earth. So the gravitational field will be directed towards the Earth. If I draw a gravitational field line here, of course it starts from infinity and it will be towards the Earth. So you draw one from here, it will be towards the Earth. You draw one from here, you can see that how this evolves. I can draw it in two dimensions, but this is actually, we need to extend into three dimensions. I'm doing it in two dimensions. Look at here. how this evolves. It's symmetric. This is symmetric. Why is it symmetric? Because we assume that Earth is a perfect sphere. If Earth is not a perfect sphere, it will not be symmetric like this. It will have the changes because of its asymmetry. So look at here. This is the gravitational field line structure. In 2 dimensions, you need to extend to 3 dimensions to get the complete picture. So this is the way the gravitational fields lines are aligned in case of Earth. So what does it mean? What does this picture? This is called a radial field. You call it radial field because the gravitational field lines are acting along the radius vectors. So we can just say this is a radial field. This is radial. That is one property. And the second property, inward. Inward means the direction is towards the Earth. So these are the two characteristics. So you can say, you can connect these two words together and say that this is inward radial gravitational field. The gravitational field is inward radial in shape. So this is the general shape of the gravitational field. And you can see that towards the Earth, the gravitational fields are coming closer and closer. So we can say that at these points, close to the Earth, you take a point here, close to the Earth, the gravitational field lines are closely packed. So this is a strong field. It indicates that near the Earth, the gravitational field is a strong field. But you take further away from here, you can see that they're spread apart. Look at here, here are all these spread apart. So we can say that further away from the surface of the Earth, gravitational field is weaker. This is a weaker field, comparatively weaker field. The further we go from the Earth, the gravitational field will be weaker and weaker. So this is the idea of the gravitational field of the Earth when observed from a distance. Now let us see a different case. So this is the radial field. If you want, I will write it again. So that's very important. So the gravitational field due to Earth is, this is radial inward. That means towards Earth, radial field. That is the description of the Earth's gravitational field when observed from far. Suppose we take a closer look at it close to the surface of Earth, the things look different. Now, let us assume that this is the surface of the Earth. Okay, here we have the surface of the Earth. If we are close to the surface of the Earth, the surface looks flat. Am I right? Of course, it is curved. But since the size of the surface you are considering is small, it looks flat. So to get an idea about the size of the surface, let's draw a diagram here. Look at here, suppose we have a house here. So you know that the size of this surface is small compared to the area of the surface. Suppose we have a small area like this close to the surface of the Earth. The field lines look different. This is the way the field lines look in that case. Look at here. I'll show you. This is the gravitational field line. They're equally spaced and parallel. Okay, this is the structure of the gravitational field line close to the surface of Earth. What do you understand from this? This is the gravitational field line close to the surface of the Earth. I'm sorry, they should be parallel and equally spaced. Look at the gravitational field line structure here, close to the surface of Earth. They are parallel and they are equally spaced. If the gravitational field lines look like this, parallel and equally spaced, gravitational field lines are parallel and evenly spaced. Evenly spaced. In this case, you call it uniform gravitational field. You call it uniform gravitational field. This is uniform gravitational field. It means, what does it mean by uniform gravitational field? It means that the magnitude and the direction of the gravitational field remains the same everywhere. What does it mean? Magnitude and direction, magnitude and direction remains the same, remains the same. When the magnitude and the direction remains the same, the lines will be parallel and evenly spaced, and the meaning is that it's a uniform magnetic field. The magnitude and the direction of the magnetic field, I mean, the gravitational field remain the same. Sorry, no, yeah, this is the idea. It will be remaining the same. So this is a uniform gravitational field. This is the case you take in the case of projectile motion. In case of projectile motion, you define that, or you assume that the gravitational field close to the surface of Earth is uniform. The typical example you use this idea in case of oh God, doesn't look nice, sorry guys. In case of projectile motion, you use the idea. Or if I write it, you will get confused. But just remember that we also make a similar assumption in case of projectile motion. So you need to remember all these points about the gravitational field, some ideas about the gravitational field lines, and then you need to know what does it mean by radial gravitational field and uniform gravitational field. So the basic idea about this is only a qualitative description about the gravitational field. Now finally, I will just want to add one significant point which may not have been written here. We want to know the gravitational field line. If you want to draw the gravitational field line at any point in a region, you need to put a small mass at that point and see which way it moves. So actually the gravitational field line, you can also add a point in here. Gravitational field line can be obtained by tracing the motion of a small body, motion of a small body. It should not be too small, definitely. Small body placed at a point. We'll write at the point because each point, if you want to draw the gravitational field line, you need to place a small body there and trace the path. Place at that point. Simply say that the path of a body moving in a region indicates the gravitational field line. So this point you always keep in your mind. So this is only a qualitative description. You should remember that this is not complete thing. It is just a qualitative description.